There are many ways to do this problem that are correct. Note that if we have 1, 2, 3, 4, 5, 6 on top, numbering the elements of our set in question, that if these are the n numbers, then these numbers are n plus 1. They're 1 bigger than the n numbers, and these numbers are 2n. This gives us an idea that we can go from these numbers to these numbers by subtracting 1 and then dividing by 2. So notice if you multiplying by 2. You'll notice if you subtract 1 from this, you get 1, and if you multiply by 2, you get this. If you subtract 1 from this, you get 2. If you multiply by 2, you get 4. If you subtract 1 from this, you get 3. If you multiply 3 by 2, you get 6. So this is a way of going from here to here. And from here to here, and from here to here. And so subtracting 1, multiplying by 2 takes us that direction. Now what takes us the other direction? What makes this one give us this, and this one give us this? Well, you reverse it. Instead of multiplying by 2 last, you divide by 2 first. And instead of subtracting 1 first, you add 1 last. So kind of the reverse order of subtracting 1 and multiplying by 2 is dividing by 2 and adding 1. Notice if you take 6 and divide it by 2 and add 1, you get 4. And so this gives a one-on-one matching of these numbers, and since this is a proper subset of this because they're not equal to each other and everything in this is included in this, then if you have a proper subset of another set and there's a one-on-one matching of them, that is one way of defining an infinite set. So this is infinite. So here's our set in question. We're trying to prove it's infinite by creating a one-to-one correspondence between it and a proper subset of itself. This is a proper subset of itself because everything in this set is contained in this one, but they're not equal because this one doesn't have 1/2 in it. So now the question is, can we create this one-on-one mapping? So if you do something to each of these numbers, what can you do to it to make it be each of these numbers? We're going in this direction first. Well, these top numbers are represented with 1 over 2n, and the bottom numbers are represented with 1 over 2n plus 2. So if we multiply by something that has 2n on top, the 2n will cancel this 2n. And if it has 2n plus 2 on the bottom, then when these cancel, we'll get 1 over 2n plus 2. So it looks as if 2n over 2n plus 2 does the job, and it does. But we learned how to factor, so we might as well factor out a 2 from the denominator, cancel the 2's, and it looks as if n over n plus 1 does the job. So to go from here to here, we're going to multiply by n over n plus 1. Let's see what that looks like. Here, n is 3, so we're going to multiply by 3 over 4. So let's take 1/6 and multiply by 3 over 4. That is 1/8. Notice 1/6 gives us 1/8. Let's try 1/10. 1/10, n equals 5, so we're going to multiply by 5 over 6, and that gives us 1/12. So this is a kind of algebraic guide to what kind of arithmetic to do to the top numbers to get the bottom numbers. Now to make this one-to-one, we have to figure out how to go the other direction. But as you might guess, the other direction can be the reciprocal of this fraction. We're going to multiply by n plus 1 over n. Let's check that out. When n is 4, we're going to take 1/10 and see what we can do to it to get 1/8. So we're putting in n equals 4 here, and we're getting 5/4. And when we multiply those two, we are getting 1/8. And so In one direction, this calculation shows us there's a matching, a mapping, and in this direction, this calculation shows us the reverse mapping, and so this is a one-to-one correspondence. There's a one-to-one match. Each one of these fractions up here, we know which one it matches down here, and each one of these down here, we know which one it matches up here. This is just one of many, 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 many ways we could do this problem, because there's all different kinds of proper subsets we could use. So one way of showing a one-to-one correspondence is to say that you could take the natural numbers and multiply each one of them by 2 and get the resulting element in the set below. The nth term times 2 gives us 2n. So that's one direction. The other direction of matching these up that would reverse that is to divide by 2. So if you're going the other direction, you can divide by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. 2n divided by 2 is n. So by using multiplication of 2 one direction and division by 2 the other direction, we've made a mapping that correlates these pairs, and it's one-to-one, and every single number up here, not just 1, 2, 3, 4, 5, but 79 will have something that it matches. It'll be 79 times 2, which is 158. And everything down here has something it matches, not just 2, 4, 6, or 8, but 1,000. 1,000 has 500 that it will match. And so every single number from 1, all the counting numbers have something down here that they match to, and all of these map back to that. So there's this one-to-one correspondence, which means in a mathematician's eyes that these two sets have the same cardinal number. Create the one-on-one pattern here. You could ask yourself the question, what can I do to these numbers that will always generate the numbers below? So 4 will generate 1/12, 3 will generate 1/9, etc. Well, the thing you could do is look over here at the general terms. What can you do to n to get 1/3? And the answer is two things. Multiply by 3, and then take the reciprocal of that. So if you were, for instance, to multiply this by 3, you would get 6. Take its reciprocal, you would get 1/6. If you were to multiply this by 3, you would get 12. Take its reciprocal, you could get 1/12. So for this direction, you multiply by 3, then take the reciprocal. What about the other direction? What can you do here? Well, you could try taking the reciprocal and then dividing by 3 to kind of undo these. So in this direction, you could take the reciprocal and then divide by 3. So let's try it. You take the reciprocal, you get 6. You divide by 3, you get 2. Take the reciprocal here, you get 12. Divide by 3, you get 4. So again, these two kinds of work create a bond sort of between these two and these two and these two, and every single number up here, including 1,000,000 and 1,000,000,000 and 1,000,000,000,000, you could always multiply by 3 and take the reciprocal and get the corresponding one down here. And if you were on that corresponding one, you could always take the reciprocal and divide by 3 and get back up here. So there's a one-to-one correspondence between these. That means they're the same type of infinity. They have the same cardinality.